Welcome to continuation of our discussion on topics in algebra. We are still treating the group theory aspect where we are using cyclic groups, and we are going to take a theorem that says the order of any element G in G divides the order of G. Now proof. We are going to use direct proof this time. Okay. Now let G be an element of the group. Okay. Such that the order of G maybe is n. Now, if G generates the whole of G, we are done, okay? We are done. Because it will imply what? That the order of G divides the same order of G. Of course, it's trivial, okay? But suppose the order of G is less than the order of G itself. Then pick some element, maybe Y in G, okay? Then and form a coset, Y. So supposing this G here, YH, where H itself is the same as that L group that generates this G, G1, G2, up to Gn. It generates a subgroup like this, okay? Then YH, the order of YH is the same as the order of H. And by definition, we know by definition of G, it has a distinct, it is, let me say, it is made up of distinct cosets. So we require G to be equal to maybe Y1H union Y2H union up to union maybe YMH, okay? Then the order of G then will be equal to the order of Y1H plus the order of Y2H, okay, plus dash dash up to plus the order of YMH. This is by Lagrange's theorem. Lagrange's theorem, okay? We know by definition of courses this is going to have. So I want to establish by Lagrange's theorem, then therefore, that the order of G, now by Lagrange's theorem, this is simply what? Therefore, order of G is M into order of YH. Why? Because Y1H, the order of Y1H is the same as the order of Y2H is the same as dash dash dash, same as the order of YMH. They are all the same by definition of cosets all the courses are the same. So, and we have m of them. So it means we can now write G, order of G, as m times the order of one of them, okay, YH. Therefore, G, the order of G by the order of H is simply M. And so, order of G actually divides order of H. But what is our H? Our H is that group generated by, no, H is that group, which we now represent as G, G1 of the Gn is equal to E, which we now call order of G, okay? And the theorem is proved. So this is, you are welcome to next presentation.